Okay, so now we're going to give you an example of how you can construct simple surfaces. In particular, we're going to introduce this idea of the connected sum. So say you have two manifolds. So given two manifolds, two manifolds, let's call them M and N, all right? The connected sum which I denote by M hash N, okay, is obtained in the following way, okay? By essentially removing a small, well, by removing an open disk, it's like from M and N, okay? And then what happens then is that you're left with, you can look at the boundary of the open disk, and then you want to basically glue the two remaining sort of circles, okay? And then you define a homeomorphism between the boundaries of the two open disks. And then you identify the corresponding points. Okay. So let me sort of give you an example of this. So before I do that, it's like let me sort of construct what is known as the two torus. So the two torus denoted T2, right, is basically the one sphere. It's like cross the one sphere. Okay, so so let me sort of show you. It's like what happens. Okay, so one way to think about the sphere, right, as we sort of saw before, is that at some interval with the endpoints identified of each other. Okay, so you want to do something similar. It's like with the torus. So with the torus, what happens is that instead of having the interval, you have the product of two intervals, right, in two different directions, which gives you something like the unit square. Okay, well, square of unit length. Okay, and then what you want to do is that you want to be able to identify the edges of the square. Okay, so as an example, if you identify these two edges together, right, then you get just a cylinder, right? So identifying this gives me what is S1 cross R, right, which is the cylinder. Well, not R, I guess it's the unit interval. Okay, and of course now we can identify both sides. Okay, so if I identify it this way and identify this side this way, and the reason why I have the arrows, it's like pointing this in way, is because this is going to tell you how I orient, how I glue, it's like these two things together. Okay, so this gives me, it's like what looks like the surface of a donut, basically, right? So this is called the two torus. Okay, all right. So with that, it's like now we can talk about, say, the connected sum. It's like of, say, two of these two tori. So let's see what happens. Okay, so I take this torus and this torus, and I want to look at the connected sum of these two things. Okay, so what that looks like, if you will, is that, as I said, you've taken open disk and you excise it. again, you cut that out. And then you have some way to identify the boundary of the open disks, right? So I'm just denoting it by this picture. So one way to sort of think about it is that you cut holes here, and then maybe you put a cylinder, it's like to glue the two of them, okay? All right, so maybe let's make that a little bit more precise. Let's imagine that you had something like a cylinder here, right? Okay, and okay. All right, so as you might imagine, and what you end up getting in essence is that you're getting now a surface which has two holes in it. Okay, so that's what we call the direct or the connected sum. It's like of two tori. Okay, so you know, so far it's like with these examples, it's like where we take a polyhedra and we identify the edges. We've done it in a way which is, in some sense, compatible. We haven't done sort of anything sort of unusual to it. Let's see what happens if you do some other less obvious things. Okay, so there's what is known as the Mobius strip. Okay. All right, so again, you take a square with unit sides or whatever. Okay, and what you can do is that you identify it's like one pair of opposite edges, but instead of orienting it in the obvious way, you can sort of orient them in this sort of opposite way. So one way to sort of think about this is that if this was a sheet of paper, you twist it and then you glue it together. Okay, and then what happens when you do that is that you get what is known as the Mobius strip. So there's a twist in the paper, if you will, and then it looks something like this. So you should try that at home. It's like, and one thing it's like you can observe is that this is an example of what is not known as a non-orientable surface. So if you look at it locally, of course, it looks like there are two sides. It's like to that sheet, right? But if you follow this, if you literally take a Mobius strip and you start drawing a line on it, right, and go all the way around, you'll find that you'll be able to actually connect, you know, back to where you started, okay, and that the line will show up on what apparently are both sides, it's like of the strip. So even though locally it looks like there are two sides, really globally there's only one side, okay. So the Mobius strip has only one side globally, and this is an example of a non-orientable surface. Okay, all right, so the next obvious question to ask, of course, is that, well, you still have these two unidentified sides, right? So you could identify these as well. And then if you do that, but if you identify these two sides with the compatible, it's like orientation, then you get what is known as a Klein bottle. Okay, so this is known as the Klein bottle. Okay, and to draw you a picture, all right, you have again this sort of reverse-oriented identification, and then the top and bottom I identified in sort of a consistent way. Okay, and then you might have seen what this picture looks like. Okay. Okay, so it looks something like this. Okay, let's just not draw this piece as well. Okay, so this is what is known as a Klein bottle, and of course, it's a two surface, but the idea is that these are not supposed to, this thing is not supposed to be a self-intersection. If you actually, of course, try to embed it's like the Klein bottle in three-dimensional space, then there's no way to avoid the self-intersection. But you can embed it, it's like in high-dimensional space without the intersection, if you will. Okay. Yeah. So anyway, so that's what's called a Klein bottle, and you might have heard about it in. Yeah. Okay. So anyway, so more generally speaking, this whole construction where you take the sides of polygons and you identify that, that's sort of a very, very systematic way of constructing an interesting class of, it's like surfaces and two manifolds. So we'll talk a little bit more about this in the context of the classification of these kind of spaces. All right, so let me stop here for now.